Welcome. In this session we will work through 10 rectifier problems, one on each slide. The circuits cover the three topologies you will meet in every examination: the half-wave rectifier, the center-tapped full-wave rectifier, and the bridge rectifier, with both ideal diodes and practical diodes that carry a forward resistance. Along the way we will calculate output voltage, load current, peak inverse voltage, output frequency, rectification efficiency, and the ratings a diode must have to survive in the circuit. Before the first problem, here is the routine that will carry you through all of them. Step 1. Identify the topology and the diode model. Half-wave, center-tap, or bridge, and are the diodes ideal, or do they have a forward resistance? Step 2. Convert the transformer data into the secondary RMS voltage you actually need. For a center-tap transformer, that means half the winding, and forgetting this is the single most common mistake in this topic. Step 3. Convert RMS to peak by multiplying by √2. Step 4. Apply the average, peak inverse voltage and frequency rules that belong to that topology. They are listed on the right of the slide. Step 5. Check your units and your diode ratings before you write the final line. Look at the reference panel and fix three contrasts in your mind. The average is 0.318 times Vm for half wave, and 0.636 times Vm for full wave. The peak inverse voltage is Vm for the half wave and bridge circuits, but 2 Vm for the center tap. And the efficiency ceiling is 40.6% for half wave against 81.2% for full wave. The possible common errors are using the full secondary voltage in a center-tapped circuit, quoting 2 Vm as the PIV of a bridge rectifier, mixing amperes and milliamperes in the final line, reporting heating power based on RMS current when the DC power based on DC current was asked for. Exercise 1 is a transformer-coupled half-wave rectifier with an ideal diode. We will have to find VDC and PIV. Supply voltage is 230 volts RMS. A 10-to-1 step-down gives a secondary of 23 volts RMS. Multiplying by √2 gives a secondary peak of 32.5 volts, and that peak is the starting point for both parts of the question. Because only one positive half sign reaches the load in each cycle, the average output is Vm divided by pi, 10.35 volts. Now the peak inverse voltage. Look at the negative half cycle. The diode is off, so no current flows, so there is no drop across the load, and the entire secondary peak appears across the diode in reverse. The PIV is therefore 32.5 volts. That is the theoretical minimum. In practice you would specify a diode rated comfortably above it. Exercise 2 asks only for the DC load current, but it is a good test of whether you understand the difference between RMS and peak. The transformer secondary is rated 24 volts, and a transformer rating is always RMS. Multiply by √2 and the peak is 33.94 volts. Across a 20 kΩ load, that peak drives a peak current of 1.697 milliamperes. Only now do we average. 0.318 times the peak gives 0.540 milliamperes. Exercise 3 is really a question about what the word power means. The 2-to-1 transformer gives a secondary of 115 volts RMS, so the peak is 162.6 volts, and across 200 ohms the peak current is 0.813 amperes. Squaring that and multiplying by the load gives a maximum load power of 132.3 watts. That is an instantaneous value, reached only at the very crest of each half sign. For the average, we take the DC component. 0.318 times the peak is 51.7 volts, which gives a DC current of 0.26 amperes and a DC power of 13.4 watts. Now be careful. 13.4 watts is the power carried by the DC component alone. If what you want is the total heating power in the resistor, you must use the RMS current, which for a half-wave sine is the peak divided by 2, and that gives 33.1 watts. Two different answers, both correct, to two different questions. Always say which one you are reporting. Exercise 4 runs the chain backwards. We are told the output must be 30 volts DC into a load resistance of 600 ohms, and we are asked what peak the input has to reach. 30 volts across 600 ohms is a DC current of 0.05 amperes. For a half-wave sine, the peak current is pi times the average, so that is 0.157 amperes. That current flows through the diode's forward resistance as well as through the load, so the required peak is 0.157 multiplied by 625 ohms, about 98.1 volts. Always finish with a check. 98 volts peak is roughly 69 volts RMS, which is a perfectly sensible secondary rating for a supply of this size. If your answer had come out at 9 volts, or at 900, you would know to go back and look for the slip. Exercise 5 is the practical half-wave rectifier, in which the diode has 20 ohms of forward resistance. That resistance sits in series with the load for the whole conduction interval, so it appears in every expression we write. The average current is Vm divided by pi times the sum of the two resistances, 50 over pi times 820, which is 19.4 milliamperes. Multiply by pi to recover the peak current, 60.9 milliamperes, and half the peak to get the RMS value of a half-wave sine, 30.4 milliamperes. For the output voltage, start from Vm over pi, which is 15.92 volts, and subtract the drop that the DC current makes across the forward resistance, 0.39 volts. That leaves 15.53 volts. Finally, the efficiency. The ideal half-wave ceiling of 40.6% is divided by 1 plus the ratio of forward resistance to load resistance, and here that gives 39.6%. A small forward resistance costs you very little. But notice that the ceiling of roughly 40% is a property of the half-wave circuit itself. No diode, however good, can improve on it. Exercise 6 is the center-tapped full-wave rectifier, and it turns on a single idea: each diode works with only half of the secondary winding. The transformer is rated 30 volts AC end-to-end, so the voltage from the center tap to either end is 15 volts RMS. Convert that to peak, root 2 times 15 is 21.2 volts. Because both half cycles now reach the load, the average is 0.636 times the peak, which is 13.5 volts. Divide by the 5.1 kΩ load and the average load current is 2.65 milliamperes. Exercise 7 is a bridge rectifier and it asks for three quantities. The 1 to 4 step-down transformer gives 57.5 volts RMS at the secondary, so the peak is 81.3 volts. Full-wave rectification means the average is 0.636 times the peak, 51.7 volts. Now the peak inverse voltage. In a bridge, the two conducting diodes connect the load directly across the secondary, so the two diodes that are off each see only Vm in reverse. That is 81.3 volts, not twice that figure. It is why a bridge needs no center tap and tolerates cheaper diodes. Finally, the output frequency. A full-wave rectifier delivers 2 humps for every input cycle, so the ripple frequency is twice the supply frequency, 100 Hz from a 50 Hz mains. That doubling is exactly why full-wave output is so much easier to smooth. Exercise 8 is a diode rating problem. A 120-volt RMS input gives a peak of 169.7 volts. Treating the diodes as ideal, the DC output is twice the peak over pi, which is 108.1 volts. But the question specifies silicon diodes, and in a bridge 2 diodes conduct in series on every half cycle, so we lose about 1.4 volts. Subtracting that first gives a more honest 107.2 volts. Second, the PIV. For a bridge, the reverse stress on each diode is Vm, 169.7 volts. Third, the maximum current during conduction is simply the peak voltage divided by the load, 169.7 milliamperes. And finally, the power rating. It is the forward drop multiplied by the average current that the diode actually carries. Each diode conducts on alternate half cycles, so it carries half the DC load current, about 54 milliamperes. 0.7 volts times 54 milliamperes is roughly 38 milliwatts, so a 100 milliwatt diode would do the job comfortably. Exercise 9 is another center-tapped circuit, this time with a 5-to-1 transformer. The full secondary is 46 volts RMS, so the half secondary that each diode sees is 23 volts, and its peak is 32.5 volts. The DC output is 0.636 times that, 20.7 volts. Now compare the peak inverse voltage with the previous exercise. Here, when one diode conducts, the non-conducting diode has the full secondary swing across it, so its PIV is twice Vm, 65 volts. Notice that this is the same peak voltage as in exercise 1, but double the reverse stress, purely because of the topology. And the rectification efficiency of an ideal full-wave rectifier is 81.2%, twice that of the half-wave circuit, because we are now making use of both half cycles. Exercise 10 is a design problem rather than an analysis problem. We are given the diodes and asked to choose the load. Each diode is rated 700 mA peak and 250 mA average. Good practice is never to run a device right at its rating, so we derate to 80%, 560 mA is the peak current we will allow. The transformer secondary is 200 volts, so the half secondary is 200 volts RMS and its peak is 282.8 volts. The smallest load resistor we can use is that peak divided by the peak current we permit, 282.8 over 0.56, which is 505 ohms. Anything smaller and the diodes would exceed their peak rating. With that load in place, the DC output is twice the peak over pi, 180 volts, and the DC load current is 180 over 505, or 0.36 amperes. Now do the check that the question implies but does not ask for. Those 360 milliamperes are shared between two diodes conducting alternately, so each carries about 180 milliamperes on average, comfortably inside the 250 milliampere rating. And the peak inverse voltage, this being a center-tapped circuit, is twice Vm, 565.6 volts. Specify a diode rated well above that figure. To close, notice what actually decided every answer in this session. It was never the diode. It was the topology. This comparison table gathers it in one place. Half-wave gives you 0.318 Vm, a ripple factor of 1.21, an efficiency ceiling of 40.6%, an output at the supply frequency, using a single diode. Both full-wave circuits give 0.636 Vm, a ripple factor of 0.48, 81.2% efficiency, an output at twice the supply frequency. The center tap achieves this with two diodes but stresses each of them with 2 Vm, the bridge needs 4 diodes but only Vm each. So the habit worth building is this. Write down the topology and the diode model first. Get to the peak voltage second. And only then reach for the average, PIV, and frequency rules that belong to that particular circuit. For practice, repeat exercises 1, 6 and 7 with the diode drops included, and resolve exercise 10 for a 400 volt transformer. Thank you.